Okay, good morning. We continue the discussion of differential equations, but before doing that, let me introduce a piece of notation which is for some reason missing from the Swedish curriculum. And that's the symbol that we use for a primitive function. So far, if you remember, when we do something in Math 4, we only have this symbol, which is a stretched S for the sum actually, and then we write integral from a to b f of x dx. Yes, and in Swedish system they call this an integral, which is of course correct. But the better name for this is called definite integral. But we do not have any symbol or any notation for just a primitive function. We just call it a primitive function, yes? In higher mathematics, a primitive function is also denoted by integral sign, but without these numbers up there. So you can write f of x dx. Yes, this is called indefinite integral. And that is what you call a primitive function for f of x. But not just one single one of them, the set of all possible primitive functions for little f of x. So in principle, if capital F is a primitive function for little f, then by this symbol we mean the set of all possible primitive functions, but they don't differ that much from capital F, they just differ by a constant. Yes, so from now on, I think it would be easier if I want to just, in differential equations, if I just want to avoid this, that would be not very wise decision. So I will use this symbol from now on, okay? So instead of saying that, so whenever you see this integral sign without these limits, and of course you respect and put d of x there to show which variable you are considering here. So when you see x is in front of d, it means the variable is x. If I have more than one letter in the expression of f of x, then d of x tells me which one is the actual variable. The other letters should be considered constants, yes? Okay, so from now on, I will free to use this symbol, even though it's not mentioned still in the book, okay? But I will try to use this piece of notation. So indefinite integral is actually what you call a primitive function. That's it. Okay, so I would say that if I take a function, differentiation will take me to f prime of x, but integration in this form, definite integration, will take me somehow back. But when I go from here to here, I end up with a unique answer. But when I want to go from here to here, I not only get f of x, I might get f of x plus any constant. Yes? So in principle, if I ask you what is the derivative of this symbol, what is the derivative of this, it becomes f of x. Because this tells you that this is a function whose derivative is f of x. Now I am differentiating it, so I definitely will get f of x. But if you have integral of f prime of x, so the operations of integration and differentiation are somehow inverse of each other. So I integrate first and then differentiate. It means that I have done nothing actually to my function. I get this same function back. But now I differentiate first and then integrate. More or less, it seems that I have done nothing. But of course, it might have that I have a constant at the end. Yes? So for example, if I ask you to calculate integral of x to the power of 2 dx, what do I mean by this symbol? I mean find all primitive functions for x squared. As simple as that, yes? So then you know that a primitive function for x squared is x to the power of 3 divided by 3, and you put a constant in front. Or for example, if I ask you what is a primitive function, what calculate this integral? They say calculate this integral, but what they mean is that find all primitive functions, yes? If I ask you to calculate this integral, this means this is minus a half cosine 2x dx. Plus c. But that's just nothing. Exactly. So if in the Swedish language, in the Swedish curriculum, I have to ask find all primitive functions for this. Another way to express this, I can say calculate this integral. They are exactly the same thing. Yes. Is that clear? Well, that's just one piece of notation that I want to use. Okay. So you know that I told you that differential equations is an actually very broad topic, and most of the time we are not able to solve given differential equations analytically. Yes. So most of the time we have to calculate the solutions to differential equations numerically. But of course we can calculate them to any degree of accuracy that we need in practical problems. But here we don't want to do many advanced differential equations, but there are some differential equations that I want to teach according to the book. So the first one type of differential equations we already discussed. Yes, for example, I give you y prime is equal to 5x. This is a differential equation, yes, because it is an equation. This equation contains a function y and its derivative, and I am looking for y. So this, if I ask you to solve this, this is extremely simple. What you do, you would say that y is the integral of 5x dx, but this becomes 5x squared over 2 plus. That's the solution of this differential equation. So if I have y prime equals to f of x, any function, even though it's a differential equation, but if you can't find a primitive function for f of x, you are done. Of course, might be the function is so complicated that we cannot find a primitive function, but that's a different problem. But in principle, if I ask you to solve the problem here, it's very simple. Y is equal to integral of f of x dx. That's it. But now today we want to talk a little bit about a very particular type of differential equation. So y prime plus a is a constant, multiplied by the function equals to 0. So I am assuming that x is the independent variable, even though you don't see it explicitly, and y is the dependent variable. So it might be in this case that Leibniz notation is probably better. So I write dy dx plus a times y equals to 0. So a is a constant, yes, is a constant, but not 0, because if a is 0, the problem is easy, yes. If a is 0, I really don't need to bother at all. So a is 0, this means that this becomes y prime is equal to 0. Then this means that y is the primitive function for 0. But what is primitive function for 0? Any constant. Yes, so that's the solution. So if a is equal to 0, this differential equation is so easy. Every constant function is a solution. But the point is that what happens if a is not equal to 0? We want to consider this y prime plus ay equals to 0. Okay, let me ask you one special case, because I think for this special case you can guess. If I give you a equals to -1, can you guess what is the answer? Y prime, instead of a I put -1, it becomes 0. I am looking for a function that satisfies this differential equation. What that function is? Yes?
ex.
E to the power of x is. E to the power of x is the answer to this one, because e to the power of x, so this means that y prime is equal to y. So I'm looking for a function whose derivative is equal to itself. And then probably this is a very famous function. It's e to the power of x, but because I'm supposed to find all of them, then this becomes this one. Yes? But be careful, here, this is different from this situation. So here you cannot say I find a primitive function for y. Yes, we don't know. Y is a function unknown. Yes, you can say that I find a primitive function for y, but y is still unknown. I want you to understand the difference. Here, I tell you that y prime is 5x, and I ask you to find y. You find a primitive function for 5x, because 5x is given as a function. In principle, if I ask you to solve this, you might say that I can find a primitive function for y, but y still is unknown. I am looking for it. There is no point. Is that understandable? Okay? So, but you need to interpret it in this way. I am looking for a function whose derivative is equal to itself. And then hopefully immediately you remember this famous function. And then, of course, if I add any constant to it, it will not change the result. So that would be the general solution of this differential equation. Why the general solution? Because this is the first degree differential equation. In the general solution, you expect exactly one free parameter. And in this answer, I have this one free parameter. So that's the general solution for that differential equation. Okay, but that is, of course, I hope that you immediately realize the general case where a is not equal to -1 shouldn't be that hard. For example, if I just give you a equals to 1 now, what will be your guess? You can guess, but I want to give you a systematic way. But before that, let us try to understand by some guessing. So what happens if I give you a equals to 1? Okay, then what you get this differential equation that y prime plus y is equal to 0. So this time you are looking for a function whose derivative is not exactly equal to itself, but is negative of itself. So can you still guess the function? It shouldn't be that far away from that guess. Yes?
E to the power -x.
Yeah, exactly. So this means that you can guess y prime is e to the power of -x, and then of course plus a constant, plus a constant c. And that's easy, yes? If I take the derivative of this function, this part becomes 0. This becomes the function itself, but multiplied by the derivative of -x, which gives me that -1 that I need. Okay, now can you guess what will be the general solution in the general case? So in this case, I considered a 1, 0, -1, and 1, but I think it shouldn't be hard to guess what will be the solution in general. Do you have any guess? But of course, I will tell you a systematic way, not just guessing, but I don't think it is hard to guess the solution here. So can you tell me what is y? Yes?
E to the power -ax plus c.
Yeah, e to the power of -ax plus c. Do you agree? Why is that? Let us differentiate this. If you don't believe that this answer is correct, I differentiate this function. The derivative of an exponential function becomes the function itself, but because of the chain rule, I have to multiply by the derivative of the exponent, which gives me -a. And the derivative of c is just 0. Yes? And then what happens? This expression is y itself, yes? So let me just write it. So this is the derivative. So the derivative becomes -a e to the power of -ax. Okay, and then I'm claiming that this is, oh, that's correct. I'm claiming that this is the solution of this differential equation. So I start from the left-hand side. Instead of y prime, I put -a e to the power of -ax. plus a times, instead of y, I put e to the power of minus x. So I will be in trouble here, yes? Because if that is y, then I put it here, then I will get an ac extra. Yeah. So let us see. This is 99% correct, but there are some problems here. So if I put y prime here, so if I take this to be my solution, probably that's not a good form of my solution, yes? By the way, I was not very careful even from the previous case. Yes, this one is not probably the correct answer. And this one is also wrong, isn't it? Because if I take the derivative of this function, it becomes e to power x. But e to power x is not equal to e to the power of x plus c. Yes? Unless c is 0. But I'm claiming that this is correct for every possible value for c. So it means that the problem is not that easy. So if I clean this c, that's correct. This is the solution. Here, if I clean this c, that's a solution. And here, if I clean this c, that's a solution. You see, that was good that we checked that. So it means that we couldn't find the general solution yet, but we were able to find at least one solution. Yes? Because if I cannot just, if I consider c, it means that I am assuming that c is not 0. Because if c is 0, of course this is correct. If c is 0 and you say this is my guess, your guess is correct. Because when I differentiate it, it becomes that. And when I put it in this equation, instead of y prime, I put this expression. And plus a times y, but that is your y. And then what happens? This one and that one are really cancelled, and it becomes 0. But if I put a c at the end, which means that I am choosing c not to be 0, and then what will happen? Of course, this will not affect this part. The derivative is still the same. But when I put y, I have to write a times e to power minus ax plus c. And then when I multiply this one, still this term will cancel that term, but a times c will survive. And that is not necessarily equal to 0, because I am choosing c. So it means that that solution is correct. But when I carelessly add 1c at the end, that was not correct. Yes? So, this means that this is not the general solution, by the way. That's a particular solution. Because this is a first order differential equation. I need to have one free parameter in the solution to be able to say that this is the general solution. So even in this simple case, I was able to find a function as a solution, but that is not the general solution. Okay, so now I want to tell you how to solve this systematically, not based on the guess. And this is a little bit unusual if you haven't had experience in differential equations. So you need to wait and see why it works. Okay, so what you do, you multiply both sides by e to the power of ax. Okay, let us see why is that good. If I multiply the left-hand side by this is called integrating factor. So this becomes e to the power of axy prime, and the next one becomes e to the power of axy. The right-hand side, of course, remains 0, because it was 0, I multiplied by that, it is still 0. But the good point is that when I multiply the left-hand side by this combination, this is the derivative of a package. So I can write it as one single derivative of a function. So can you tell me, can you see what function is that? So the left-hand side, what I'm claiming is that the left-hand side can be written something derivative is equal to 0. Now, can you fill up this question mark? Put something instead of this question mark so that when I differentiate it, it will generate this underlined expression. Yeah, it's not hard, but you need to think about the product rule. Let me write it and then check if that's correct. Okay. So the question mark should be filled up with this expression. Let us check if it is correct or not. That's a product of two functions and I want to differentiate. So what should I do? I have to differentiate the first one, which hopefully you agree with me, it becomes a e to the power of ax. This is the derivative of the first one. I have to multiply it by the second one, which becomes 1. Plus the first one multiplied by the derivative of the second. Yes? And then if you compare this one with the expression underlined there, they are exactly the same. Yes? So this means that this was the trick. Of course it was not easy if you don't have experience. So how should I understand that if I multiply it by e to the power of ax, it becomes a derivative of one single function? But understanding why it works is not hard. Guessing that trick might be a little bit hard, but understanding the trick is not hard. So is that understandable? Okay, now I have a package whose derivative is 0. So this means that this function is a constant function. Yes, so what happens, it means that e to the power of axy is a constant. Yes? And then I am looking for y. So I have to divide, I have to make y alone. Yes? So y becomes c divided by e to the power of ax. And then I bring it up. And this is why we missed that c. We had the c in the wrong location, you know. So e should be c times e to power minus x. And can I consider this the general solution of this differential equation? The answer is yes. Because a is already given to me, so that's a constant. But you see that I have another constant in my solution. How many constants I have? I have one free parameter, and the order of differential equation is 1. And this also satisfies my equation, so I would say that this is the general solution. Yes? Now, if you don't believe, we can test the idea. Let us really check, because you see, I was in trouble when I put the c on the wrong place. I got it wrong. But the position of c should be as a multiplicative constant. So let me now check. I want to check that this expression, this function, independent of my choice of c, will satisfy this equation. So what I have to do, I have to differentiate it. This is a constant. I have to differentiate this one. It becomes the same function, but I have to multiply by the chain rule the derivative of this one, which becomes minus a. Okay, so now the left-hand side is equal to y prime, which is this expression, minus a times c e to the power of minus ax plus a times y. But this is my y. If I multiply it by a, it becomes a times c e to the power of minus ax. Now you see, whatever c is, this and that are cancelled and I get 0. And that's equal to the right-hand side. Yes? Is that understandable? Yes or no? Is there any questions? So what we learned is this. What we learned is that if I give you a very simple differential equation, by the way, it's very common in the topic of differential equations, they consider differential equations case by case. Usually the differential equations appear in science, engineering somewhere, and then mathematicians become interested in solving that differential equation. They also treat differential equations under different categories, but they also study differential equations case by case. So that is one of the differential equations that we know its solution. And so it means that you need to remember this form of this differential equation. If the derivative and a multiple of the function are involved, equals to 0, then the solution is that one. The way that I presented here is the way to derive the solution. But of course, if the solution is given, it's a matter of seconds to check that this is the correct solution. Yes?
This trick of multiplying e to the power of ax, how do you, for other functions, can you still use this trick?
No, not that much. I mean, if there is a factor that when you multiply into the differential equation, it turns the expression into the derivative of one single function. That expression is called an integrating factor. Okay, and the question is that, your question is that, can I have an integrating factor for other sorts of differential equations? Yes, some of them have, but some of them doesn't. And then you have to find another way. Yes? Okay, so the book is actually talking about this, but let me ask you this question now. So let me immediately give you an example. So what the take-home lesson, what we have, if I want to summarize that, we had a differential equation, we were able to find its general solution. That's it. So that was the goal. And then how we did it, we multiplied it by this integrating factor. Okay, so for example, if I ask you to solve this initial value problem, so initial value problem that I have is this. I have, for example, y prime plus 1/2 y equals to 0, and I tell you that y of 0 is supposed to be 5. So I want you to solve this initial value problem. What do you remember? What is initial value problem? Initial value problem is a differential equation together with one or more extra conditions for some points. So you are supposed to find that constant. So these initial conditions are given to you because you are supposed to find this c. Okay, so as soon as you see this is in the formula sheet. So you really don't need to start from scratch. This is one of those famous differential equations that you have, but you need to realize that this number now is playing the role of a. Yes? So then I know the general solution is a constant c e to the power of, what was that, minus a times x. So that is the general solution. Yes? But y of 0 is supposed to be 5. What does it mean? It means that if I go to y and replace x with 0, the answer is supposed to be 5. So this means that 5 is equal to c e to the power of 0. So this means that c is 5. And then I put them into one equation and I get y is equal to 5 e to the power of minus 2, 1 over 2x. So what does it mean? It means that I was able to find a solution for this differential equation that also satisfies this extra condition. That's the only function with that problem. Okay, now let me increase the level a little bit. What happens if this is not 0? For example, let us make it 1. So let me just take a simple equation. Can you guess a function which satisfies this differential equation? When I add the function to its derivative, the answer becomes exactly 1. You see that even if I change it slightly, guessing is not that easy. Can you guess? Not just a random guess. If you think wisely, you should be able to understand it. How can I find that solution? Of course, one solution is extremely simple to guess what that solution is. So I want you to write y equals to something that satisfies this equation. What is that? Extremely simple guess, by the way. Yes?
Y equals to 1.
1. Y equals to 1, it works here. Yes? If you take the derivative of 1, what is the derivative? It becomes 0. So you put 0 plus 1 is 1. So you shouldn't ignore this. That's also a function, but that's a constant function. It's an extremely simple function. But if I ask you, can you guess another one? Or in other words, are these the only solution? Or you can also find other solutions. You might guess that I should also be able to find other solutions, because can I call this one a general solution? No, because this is the first degree. When I say that I have the general solution, I expect to have a free parameter in my solution. There are no free parameters. That's just one constant 1. So this is a particular solution for this differential equation, but that's not the whole story if I am interested in finding all solutions. Okay, so can you think how to do it? Any other guess except 1? Somehow I want you to think in this way. Y prime plus y is equal to 0. If I ask you what is the solution to this, you can answer. Yes? What is the solution to this one? A is 1. I can use that formula. So this becomes 1. Y equals to c to the power of minus x. But you might say that this is not good, because this is the answer to this differential equation. This means that when I put this expression here, I get 0. But on the other hand, you tell me that I want a function so that when I put it here, I get 1. Can you fix the problem? What Elias said actually, and what I said on the board, can be combined to give you the real solution, the general solution. Can you see that? So you see, this solution. This is the solution to this one, and that is the solution to this one. Okay, can you tell me what's the solution to this one now? The general solution. This is of course one of them, but I want all of them. Should I write? Yeah, I will write, okay?
Oh, wait.
So that's the general solution, isn't it?
Yeah.
Because it's clear, because if I ask you to differentiate this, the derivative of this consists of 2 parts. Yes? So when you put this in here, when I differentiate this one is gone. and what I get is the answer to the 0 one, but in the next one that I bring y in, this will compensate, this one that I have put here will compensate for that one. So that's the general solution. Can I consider this the general solution? Yes, because it is a solution. If you don't believe, we can check it. It's a solution, and it contains one free parameter. So this is a general solution. If you want, I can check it. Y prime is equal. If I differentiate this, it becomes minus c to the power of minus x. Now let us put y and y prime here. So the left-hand side becomes equal. You see what happens? This y prime plus will cancel that part of y, but there is one left, and this is gone, and I get 1, and that's the right-hand side. Yes? But now, so what I'm saying is that is good. If you can solve this problem, which we could, might be for this one you can guess something, and what you need to do is just to add your guess to the general solution of that one. You will get a solution for this one. Is that clear? Okay. But of course, it might be hard to guess. So still, we need a systematic way to solve the problem. Let us see if the idea of integrating factor will also work in this case. Okay, can you tell me, if it is going to work, what is your suggestion for the integrating factor based on the experience you got so far? So do you understand what I mean? My question is that this solution was based on a little bit of guesswork. But if I want to solve it systematically, my question is that, do you think that I will also have another integrating factor for the new situation? And what is your guess about the probable form, a possible form for integrating factor based on the experience you got there? So do you have any suggestions? I want to multiply both sides by something. Okay, can you tell me what that something is? Yeah, just dare to guess. What should I write? E to the power of something, yes? So what should I write? E to the power of what? At least you have a guess. What is a in this case? A is 1. So why not? Let us check e to the power of 1x to see if it works. Yes? So I multiply everything by e to the power of x. So this becomes e to the power of x y prime plus e to the power of x y. On the right hand side I have to write e to the power x. But can you see that the left hand side is a prime of a question mark? The right hand side I cannot do anything. I have to keep it. But can you tell me what can I put instead of the question mark now?
The product rule.
Yes? So what should I write instead of question mark?
E to the power of x multiplied by y.
Exactly. If you don't believe, let us check. The first one multiplied by the derivative of the second one will give me this term. The derivative of the first one, which coincidentally is the same, multiplied by the second one will give me that term. So this means that I know what is the problem. The problem, this question mark is a function whose derivative is e to power x. So what does it mean? It means that e to power x times y is a primitive function for this. Yes? But finding a primitive functions for e to power x are super simple, yes? So what is the set of all primitive functions for this? Are e to the power of x plus a constant. But now I want to make y alone, so I have to divide everything by e to power x. When I divide everything by e to power x divided by e to power x gives me 1. And then c divided by e to power x. But there is a better way to write it. I would write it 1 plus c e to power minus x. And that was exactly what we guessed. Yeah, is that understandable? So the method of integrating factor, actually, so you realize something. For example, if I change this to a function now, the guess becomes even harder, yes? So for example, if I give you this differential equation, do you have any idea? So I will give you y prime plus 3y equals to so let me write e to the power of 4x. So let me write 3. Well, let me write 1/2 e to the power of 4x. So assume that I ask you to find the general solution to this differential equation. So do you have any guess where I have to start? Because you see that, I hope that you understand, the notion of integrating factor doesn't depend on what comes on the right-hand side. Yes, because when you are looking for an integrating factor, you multiply both sides. So whatever you have on the right-hand side, it doesn't matter. Of course, if the integrating factor is more complicated, what you get at the end will be more complicated. But the form of the integrating factor depends on the form of the left-hand side. And yes?
I have a guess.
Yes?
E to the power of 3x?
Yeah, e to the power of 3x. Because you saw that in the general case when I was solving this, of course in that case I had 0 here. But this is not that important when it comes to integrating factor. What matters is that when I multiply the left-hand side becomes a complete derivative. So, and I already know that the left-hand side of this matches with the left-hand side for this, except that a has been replaced with 3s. So if the integrating factor was e to the power of ax, it's a good at least guess to see that the integrating factor, it would be e to the power of 3x. And let us just do that. So what I do, I multiply both sides by e to the power of 3x. But if I multiply this by e to the power of 3x, it becomes e to the power of 7x. Yes? But now, can you tell me again, what can I put in the question mark here? The right-hand side is just copy and paste. But what can I put instead of the question mark here? A function whose derivative is this underlined expression. What is that? You have it here on the board, yes. You did it for the general case where a was 3, where a was just a. Here a is 3. So this becomes what? E to the power of what? 3xy. And if you don't believe, you can check it. The first one multiplied by the derivative of the second one gives me this term. And this one multiplied by the derivative of the first one gives me 3e to the power of 3x. That's correct. And then this means that I am looking for this question mark. So this means that whatever is inside this is nothing except a primitive function for this. And this is also very simple to calculate. Yeah, but in Math 4 we just say primitive function. In this language I am using this symbol, meaning primitive function. So this means that e to the power of 3xy is equal to 1 over 4 is a constant, but I hope that you remember a primitive function for this is 1 over 7 e to the power of 7x but plus a constant. Okay, and then this becomes 1 over 28. So e to the power of 3x y is 1 over 28 e to the power of 7x plus c. And I want to make y alone, so I divide everything by e to the power of 3x. this becomes 1 over 28 e to the power of 4x plus c e to the power of negative 3x. So that is actually not easy to guess. Yeah, so we solve it systematically. So this means that at here we can claim that we found all solutions to this differential equation. And that is the general solution. Why? Because in the solution you see a free parameter c, and what is the order? It's also 1. So the number of free parameters matches with the order, so we are done. Is that clear? Any questions?
But
Hmm?
you wrote 1 over 2 e to the power of 4x, but then you changed to 1 over 4.
That is my mistake. So what do you know what I do? I will change this to 1 over 4. Yes, that's true. Because my solution is based on 1 over 4, yes? Am I right? Yes, everywhere I use 1 over 4. So let us just make it 1 over 4. Thank you very much, mate. I don't know why I made it 1 over 4. Okay. So now I want to draw your attention to some point. If I have given you this problem, but instead of making it this, so what I'm saying is that let me ask you this question. Y prime plus 3y, that's the same as before, but apparently I will make the right hand side simpler for you. Okay, x. Okay, so in principle this looks simpler than that one, but you will see this is harder than that one. The reason becomes clear when I want to do the same process. Okay, so let us see why. This is something, if we have time, I see some of these tricks in the next chapter of Math 5 on the problem solving. So might be I will also continue teaching those parts. So let us see how it goes. But here, let us see why this becomes harder. Even though what you expect, you might expect that this should be at least at the same level or even simpler, because x is a simpler function than 1 over 2 e to the power of 3x. Okay. So let us just do that. So do you have any suggestions for this one now? Y prime plus 3y is equal to what? Is equal to x. So do you tell me what to do now again? I hope that you have enough experience. Tell me, okay? If you are not that affected by that 1 hour, yes? Are you sleepy? I don't know what is this. We have to switch the time, you know. Is it a good idea? Yes? I was actually shocked. I was working in peace, then I realized that, okay, my phone clock is different from what I have on my wrist, you know. And so what we have to do here? Tell me. Okay, tell me something, yes?
I mean, normally you would want to multiply by e to the power of 3x.
Yeah, exactly. That's the integrating factor. So I will multiply that e to the power of 3x y prime plus 3e to the power of 3x y. But the right hand side I have to multiply as well. But this remain like that. Yes? But the left hand side is as before, e to the power of 3x y prime. On the right hand side I have this. Then the problem is as before, so I have to find a primitive function for this. E to the power of 3x, y is the primitive function for this function. Then you are in trouble. Because you don't know how to find a primitive function, do you know? If I ask you what is a primitive function for this one, can you answer? What is a primitive function for this? Can you find a function whose derivative is this? And I hope that you don't make this mistake writing x squared over 2 1/3 e to the power of 3x. Yes? This is nonsense, yes? I told you that if I have a product, I am not able to find the primitive functions for this part and for that part separately. We don't have a rule for a primitive function for the product. or not at least a simple rule. And then, so this is not the case. Can you find a function whose derivative is this? This is a little bit more advanced. It's not that easy to find. You haven't studied that. It's not hard, but you haven't studied a systematic way to find a function whose primitive function is this function. Yes? If you can guess, of course, that's okay. If you can guess the function whose derivative is x e to the power of 3x, then you are done. You solved the problem. That is the reason that I consider this problem harder than the previous problem. Because in the previous problem, you see, on the right-hand side, I had e to the power of 4x. When I multiplied it by e to the power of 3x, that e to the power 3x was absorbed in e to the power of 4x and make me an exponential function, and I know a primitive function for exponential functions. But in this problem, because I have x on the right, when I multiplied it by my integrating factor, there is no way to absorb this into that. I have to live with both of them. Yes, x e to the power of 3x. Then it means that finding a primitive function becomes hard. Yes? Okay, did you come up with a guess? What is a primitive function of that? So in principle, if I want to solve this problem at this level, I will leave this alone. At least you reduce the problem to a very specific question. So y is equal to, I divide everything by e to the power of 3x. Then I would write x e to the power of 3x dx. And of course I have a constant. Then it becomes c to the power of minus 3x. So by writing this, you didn't solve the problem in full details because still this is not known. But at least you understand that the only unanswered question is this. If you can answer this question, then you know the answer. Yes?
Can't you use a product rule for x and e?
No, we don't have a product rule for primitive function. That's the point. I told you before. I wrote it in that way, if you remember. Primitive function for f plus g is primitive function for f plus primitive function for g. That is true. But primitive function for f times g, we don't have any formula for that. And then I wrote primitive function for f times primitive function for g is not the correct one. Unless you make a rule. Yes? There is a version of the product rule for primitive functions. We might be able to get time because I see that there are some parts for interested students at the end of the book, and might be we can cover some of those parts without having exam for them, of course. But let us see how it goes, okay? But the point is that this is not possible. At this point, either you should have a pure guess or you have to wait to see how it goes. Okay. So I clean this because in principle, can you guess a function whose, I don't know, even I cannot guess, I have to calculate. Let me see. So 1/3 of x e to the power 3x and minus, for example, e to the power of 3x. Do you think this will work? You? That might be So let me calculate it. It's not easy to guess. So this is u dv. So this means that this is 1. Yeah, so that would be, I think, this one. So for example, if I give you this function and I ask you to differentiate it, let us see what happens. The derivative of the first part is the product rule. It becomes the derivative of the first one multiplied by the second one. And then plus the first one by the derivative of the second one. Yes? Oh, sorry. And then this one is minus 9, 3 e to the power of 3x. But then if I simplify, it becomes 1/3 e to the power of 3x plus x e to the power of 3x. And this one and that one will be minus 1/3 e to the power of 3x. And then suddenly this one and that one are gone, and this function is left. So that is correct. So this is a function whose derivative is x e to the power of 3x. But you see that I couldn't guess. I cheated a little bit here, and I was able to find a solution. Okay. But now, let me go back to this method. It is still on the board or not? Yes, it is. You remember, so we were able to guess at this level. So you see, if I want to do guesswork at this level, it was not easy to guess. Because I have to guess a function whose derivative is this guy, which is hard. But let us do the guesswork in the beginning, using the same trick. So you see, I would write y prime is equal plus 3y is equal to x. If I give you the solution to this one, if I ask you to solve this, you already know the solution. It's still on the board. That's the formula. So it becomes y equals to c e to the power of minus 3x. Okay? But instead of doing the guesswork at the very end, which is possible but hard, can you do the guesswork here? Can you guess a function that satisfies one single function, not a complicated function? Can you guess a function which satisfies this equation? And then give me a solution to this one. It's not hard to guess. Huh?
Can you just add x, like with the one before?
So you give me a function. What can I write so that when I put it here, the left-hand side becomes
c
x?
times e to the power of minus 3x plus x.
For here?
Yeah.
No, because x doesn't work. If I put x here, this becomes 1 plus 3x.
No, not x. C.
No, I understand, but I have to have a guess here. Then what I guess here, then I will add it here. This becomes a solution to my problem. I understand what you mean. You are saying that add this one to x. No, this will not work. Because if I take this one and put it here, this part will give me 0. Yes?
Yeah.
So this means that this part should give me this, which will not. So that's what I'm saying. If we can have a guess here, but you are right at the end. If I can find a guess here, then I take this guess and add it to what I know here. Then this becomes the solution for the whole thing. I will treat them systematically later, but I just want to pique your curiosity a little bit. I mean that even for this simple case, you see, so we are doing something. When we are solving the problem, we are really doing something, yes? Because guesswork is not that easy. Okay, can you have a method for guessing your function? Can you present, of course, this is, might be we cannot do that. Everything that I am talking, by the way, are parts of the tricks that we learn. This is the way mathematicians have thought to be able to find these methods. So if I ask you to guess one single function, not all functions, if I ask you to guess one single function for this, so I don't want to be completely generic, but you couldn't guess. But can you present a little bit reasonable way to help you to guess? For example, can this function be trigonometric function? No. Because if I have sine and cosine involved in this function, when I differentiate them, sine and cosine will be left somehow with a little bit different combinations. And then when I add them at the end, I would expect a sine or cosine function. But I want to have one x at the end. Is it reasonable to guess an exponential function? No. Because if I have an exponential function and put it here, the derivative of exponential function is exponential function. That's also exponential. So I will have the sum of two exponential functions. So it cannot be x. So try to rule out some possibilities. So what type of functions do you expect, if any, will satisfy this function? Is that this differential equation? What type of functions do you expect? So do you think logarithmic function will work? Clearly no, yes? Because logarithmic, I mean ln function. Ln function, I differentiate it, becomes 1 over x. So somehow x goes to the denominator. But I want to have x. So we have to forget about logarithmic functions as well. So what is the most reasonable function that satisfies this? What type of function it should be? Trigonometric is not a good guess. Logarithmic is not a good guess. Exponential is not a good guess. So what is left? The simplest possible functions, yes? So what are the possible exponential functions? No. Trigonometric functions? No. Logarithmic functions? No. So what type of function is left?
I forgot its name
Yes.
in English, but x to the power of something.
Yes.
So a constant number.
Yeah, polynomial functions.
Polynomial.
Yes, they are polynomial functions. But polynomial functions could be of high degrees or low degrees. For example, x to power 2, x to power 3, x to power 100. Which degree do you expect to appear? For example, can you expect to have a first degree?
Maybe.
Maybe. But can you expect a third degree? Third degree is not reasonable. Why? Because when you have a third degree, when you differentiate it, it becomes second degree. Yes? But what is on the right is just one first degree. So, I mean, we have some thresholds. So, third degrees and higher are probably not useful. So, it means that I have some doubt about the first degree polynomials and second degree polynomials. Yes? So, do you think first degree polynomials will work? We don't know. But what is the most general first degree polynomial is ax plus b. Let us check this. Is it possible to fine-tune a and b so that this will fit this equation? This is not hard. Because what is, in that case, a prime is a. And I put it back into this equation. This becomes a plus 3 times ax plus b. I want to fine-tune. I am not going to find the best solution. I want to just be able to guess randomly, at least, not randomly, systematically one solution. That's enough. Okay, so how can I solve the problem here? Then it means that, is it possible to find a and b so that the left-hand side becomes x? So what is this? So I would write 3ax plus 3b plus a. I want to make it x. This is a scratch work that I am doing. I'm trying to help myself to guess. and then realize this becomes a very powerful tool in solving these kind of differential equations. Can you see what should be A and what should be B so that the left hand side becomes exactly X? It's very simple now. You want to make this equals to X, and that is up to you to decide about the particular values for A and B. So what is the good choice for A? Hello?
I'm thinking.
There is nothing to think. 3ax, you want to make it x. So what you should choose for A?
1/3.
1/3. Let us guess. 1/3 will fix that. But then unfortunately when I choose A equals to 1/3, so this becomes 3b plus 1/3. I have to get rid of it. And that's also, so I want to choose B in a way to get rid of it. So B is minus 1/9. Because I want to get rid of it. Get rid of it means that I want to have it 0. So this means that B is minus 1/9. Yes? So B should be minus 1/9. A should be 1/3. Then this becomes identical to X. So I was able, it was hard to guess. By the way, I myself couldn't guess. But even though I am guessing something, but that's an educated guess because I realize there is no hope for looking for sine functions, cosine functions, logarithmic functions. Let us look for polynomial functions. And then I realized that there is no point to go to higher degree polynomials because I want to have x here. But I was not able to guess that 1 degree polynomial, the first degree polynomial. I told myself that whatever that polynomial is, it should be of this form. And then I put this back here, then I calculated, not just guessed. So I guessed the form, but I didn't guess the details. I calculate the details. So this means that what is your answer that you couldn't guess? It is 1/3 x minus 1/9. This is why you couldn't guess this function. If you don't believe, let us check. Let me calculate y prime. Y prime is 1/3. And I put it on the left-hand side. The left-hand side is equal to, instead of y prime, I put 1/3 plus 3 times the function. Yes? And then when I multiply 3 in, it becomes x minus 1/3. And you see that these are cancelled, and I get x. Okay, now what Ruben mentioned is correct. So this question mark now is clear. This question mark is 1/3 x minus 1/9. And now if I ask you, can you solve this problem? You would say yes. So the general solution to this problem is this general solution plus the particular solution that I got here. Okay? Okay, so don't consider this lesson a very systematic lesson. I just wanted to motivate you that even for very simple differential equations, there are actually plenty of things that we have to do to be able to solve the problem. But the next time I will actually more or less review what I have written on the board in a systematic way. Okay? The only thing that we did it really systematic, and unfortunately I erased that, we got a formula. So that formula is the general formula for this. If you have this differential equation equal to 0, then we were able to get this general solution. This is done properly. But the interesting problem is, what happens if I have non-zero terms on the right-hand side? I have functions. And then we also learned that if I have an exponential function of this form on the right, I will not get any problems because I know how to calculate. In general, I will not have any problems if I know how to calculate higher level primitive functions. Yes? So this, we can understand this problem in two different ways. Either expand our knowledge about finding primitive functions of more advanced functions, or we also, both of them are done. So in mathematics in the future, you will also learn this, and you will also learn how to do some educated guess. Okay? But next time I will treat them a little bit more systematically. But I just wanted to motivate you, even for a very, very simple differential equation like this, there are many things that we have to understand. Any questions? Okay, thank you. Yeah, we can end the meeting now. Thanks.